So we have this article here modeling a pump startup event. So the reason why there's a separate article on this is because there's some additional little tricks involved because of the fact that you need to enter the rated head and flow of the pump in the initial conditions. Because in the initial conditions you'll have your pump off. And since Hammer needs to be able to construct that 4-quadrant curve based on your nominal operating point of your pump, you have to enter manually that operating point. So if I jump over to Hammer for a moment, there's actually a pump startup sample file that I put together a while ago that ships with Hammer, and it's just a variation of one of the water gem samples. And you'll see in the properties of the pump that the pump type transient is set to pump start, variable speed torque. And you'll also notice that there's these two additional fields shown here, flow nominal and head nominal. So these are the ones that you enter to basically specify what would normally be specified in the results, flow and head, if the pump were initially on. So what you would do is run maybe just a quick steady state to see during your normal operating conditions when the pump is on, what would be the flow and head. You would grab those and then paste them into the flow nominal and head nominal, then turn the pump off. And now you're ready to model the pump start. So just like with the variable speed option in the pumps, and also what we saw for valves, you basically have a pattern where you're telling the pump what to do over time. So contrast to the emergency pump shutdown where you just enter one number and it assumes that it just instantly cuts off the electrical torque. With the pump start, you have to specify, how quickly it's able to ramp up. So you'll notice here the control variable is set to speed. So the pattern here is multiplying against the full speed in the pump definition. So when we say 1.0 multiplier on the pattern, that means 1.0 times the initial, not the initial, but the full speed that you enter in the pump definition. So basically at 10 seconds, the pump impeller speed is up to full speed. So it takes 5 seconds for it to do that. Again, be careful about this and realize that if you're flipping the switch, so to speak, it takes some time for the actual impeller speed to get up to full speed. So one thing to consider would be to use, instead of speed for the control variable, you would use torque. And then in your pattern, you can just say, between 5 and 5.1 seconds. It's just a sort of an instant on, and then the pump impeller will start to spin up based on the inertia. So that's the main way that you set up a pump startup. Now the reason why there's so much other information in that article is because of the complications that can occur because of the fact that the initial conditions has zero flow. So you can imagine a network that maybe doesn't have a tank here. If you turn your pump off, then there's nothing to supply those demands, and you would run into issues there. There are also some other little things that could result in basically an unexpected operating point in your final steady state. So you might enter a certain head and flow for your nominal head and flow, but maybe once you actually run the transient simulation and see what happens at the end, you would maybe expect that it would be operating at this exact flow and head, but that may not necessarily be the case for many different reasons. One of them could be maybe the tank is filled and drained a little bit, so the conditions really aren't the same as what they were when you grabbed these values from a steady state run. Another problem that I should probably cover here is in the way that Hammer calculates friction factors and uses them for a pipe. So this is actually a good topic here. So in the properties of your pipe, normally you're entering it using the Hazen-Williams method. So you're entering a Hazen-Williams C factor, something like 120 or 100, something like that. But Hammer, the transient solver, always uses the Darcy-Weisbach method. So it's using a roughness height, and it's ultimately using a Darcy-Weisbach F factor. So what it has to do is do a conversion, and the way that it converts is not directly from the Hazen-Williams C, but rather from the computed initial head loss. So if I compute this model, initial conditions, you'll see, for example, in the pipe next to the pump, well, we have zero flow, so there's zero head loss. So in that case, the program does something a little bit different, and it actually does directly convert the Hazen-Williams C factor, or if you happen to be using Manning's for some reason, it would convert that to the Darcy-Weisbach F factor. There's an equation that converts there. So because of that, you can run into issues where there's a case where it's somewhere in between, where the flow is just small enough to induce a little bit of head loss, but the head loss is basically zero out to as many decimal places as you can. And that's a problem, because if Hammer sees a non-zero flow value, it will try to take the head loss calculated in that pipe to come up with the Darcy-Weisbach friction factor. And this is based on a calculation option here under Transient Solver. You'll notice there's a flow tolerance. Let me add some decimal places to this. So this is the flow below which it uses a different method to come up with that friction factor, and basically considers that pipe as having zero flow. So if the flow is above this value, let me put this in gallons per minute. So it's a very small value, but basically if the flow is less than this value, then it directly converts the Hazen-Williams C to a Darcy-Weisbach F. But if the flow happens to be just a little bit above this, for example, it will try to convert the head loss through that pipe to the Darcy-Weisbach F, and that head loss may be exactly zero still, even with that tiny flow, which means it's going to result in a Darcy-Weisbach F of 0. And in the case of a pump start, that means it's a frictionless pipe. Whereas, when you were to run this initial conditions where you grabbed the nominal head and flow, obviously there was some resistance through that pipe. It was not, perfectly smooth. So that's another reason why your ending transient results may not match the nominal operating point that you enter for the pump because of things like that. Well, how do we know if that kind of problem is happening with the Darcy-Weisbach F? Well, you would check that under Report, Analysis Output Log, and actually I have to enable that here. So there's a calculation option under Transient Solver called Generate Extended Output Log, and that needs to be set to true first before you even get that report. So let me run the model. So as I mentioned, so if you have this Generate Extended Output Log set to true and you go under Report Analysis Output Log, that's going to open a text file. And if you do a search here for pipe info, that'll bring you down to the right section, pipe information. So this shows you some basic information about what Hammer is using during the transient simulation for that pipe. So it has the the length, the diameter, wave speed, and the Darcy-Weisbach friction factor. So you can see in most cases it looks pretty good here. So if you had a case like I was saying where maybe the flow was just a little bit above that flow tolerance, but the head loss was exactly 0 because the flow was 0, then you would see a 0.000 in this list, and that would tell you that you need to take some action there and fix it. So that might amount to maybe adjusting the flow tolerance, or maybe even adjusting the initial condition solver options to balance at a more accurate solution. So basically, when you're computing initial conditions, the steady state, it's trying to balance energy across the model and converge on a balanced solution. And it's not going to be exactly perfect. I mean, even if you have a pump that's off, if we were to take a look at this pipe here, you can see there is still a 0.0001. There's a tiny flow still there, and that could be considered numerical noise, basically, as a result of the convergence. So the model has converged at an appropriate tolerance, but there is a tolerance. It can't be a perfect exact 0 in all cases. So sometimes there's a little bit of fuzziness, a little bit of noise, so to speak, in these numbers, and because of that, that can mess with things like this, comparison to the flow tolerance. And my point there is that maybe you can make an adjustment like add another 0 to the accuracy for your initial conditions to try to balance on an even more accurate solution. Even if it takes a few more trials, maybe you'll get a flow that's a little bit closer to 0. Didn't really have an effect here, but you can do things like that, and that's a lot of what that pump startup tech note goes over. But the same thing also applies if you're using a valve and you're modeling a valve opening. So if you're starting your initial conditions with the valve closed, all the pipes will have 0 flow probably, and you could run into the same issue. So it's a good idea to be aware, again, under Report, Analysis Output Log, go down to the pipe information section and double check that your DW friction coefficients are good.
If you found this video helpful, please give it a like. If you want to see more such series, consider subscribing to our channel. Thank you, and see you next time.